folks, welcome to some examples about rational exponents. Now this section isn't from the book, so your homework's just going to be a worksheet. And when you hear a phrase like this, rational exponents, right? Rational, we've talked about, it's got that word ratio in it. So we're going to be talking about exponents with fractions. So things like, how do you deal with 9 to the 1/2, right? You have a rational exponent because 1/2 is the exponent and it's a fraction, right? It's a ratio between two numbers. So we're going to look at exponential notation when you have nth roots, right? Right here was a square root. What happens when you have a cube root, a fourth root, a fifth root, right? And then we're going to take a look at expressions that extend beyond when your numerator is just 1, right? We'll look at some number, a, your base, to the m over n. We're going to really practice converting between radicals and rational exponents, right? We want to be able to go each direction, meaning if I had a radical, I could switch it over to an expression with a rational exponent, and if I was given an expression with a rational exponent, I could switch it back to radicals. And then we're just going to keep on using these rules, like how do you deal with exponents and rational exponents, right? So, or exponents when they're specifically rational exponents. So let's start with the simpler version of a rational exponent. Not to say it's simple, but it's simpler when that numerator is just 1. So in all of the examples or all of the options in example 1, right, A through F, every numerator is going to be the number 1. All right, so we're going to start with that version of a rational exponent. We're going to build up to when your numerator is something other than 1, but for right now, it's just going to be 1. And here is the relationship between that radical and that rational exponent, right? So when we talk about converting between radicals and rational exponents, if you have the nth root of a number, right, and it's got to be a real number, right, then a to the 1 over n is equivalent to that radical expression. So just so we're clear, right, this is an expression with a rational exponent because, again, the exponent is a fraction. This is a radical. So when we talk about converting between radicals and rational exponents, here's one version of it. And again, the simpler version, not to say easy, but this is simpler when the numerator is just 1. So we're going to take a look at a bunch of rational or expressions with rational exponents and convert them to radicals, and then just kind of play them out and solve them or simplify them and see how we're doing. All right, so if I see something like this, let me scooch my paper up so that we can see all of it. Right, so if I see something like 8 to the 1/3, take note that that numerator is 8 and that denominator is 3. And the denominator is what gets mapped to the index of your radical, right? So whatever this denominator is here, it becomes the index of your radical. So if I have 8 to the 1/3, this will then turn into the cube root of 8. Right? And so that's that relationship. So keep in mind, because we're gonna change this numerator before too long, right? It won't always be the number 1. But start to map out whatever the denominator of your fraction is. Whether the numerator is 1 or anything else, whatever the denominator is, it becomes the index. And then it's a matter of solving this or simplifying this expression, right? 8 is 2 cubed. And when you have the cube root of a number cubed, those are inverse operations of each other, so they cancel out, and that leaves me with just the number 2. So 8 to the 1/3 is like saying, hey, find me the cube root of 8, which is just the number 2. Over here for B, you can see my denominator is 2. That will become the index of my radical, right? So I'm going to have the square root of 9. All right, so 2 mapped to the index. Usually when the index itself is 2, we tend not to write it. It's implied. All right, and the square root of 9, well, we know that is the square root of 3 squared. When your index and your exponent match, there's a cancellation, so this just simplifies to 3. Okay, so let me scooch the page up just a wee bit, and then let's get going on some other examples. So things to take note of for C, right? And I really want to compare and contrast right now C and D. Take note that in C, the negative is outside of the parentheses, right? It's just 81 that's being raised to the 1/4, and over here the negative is inside the parentheses and is also being raised to the 1/4, and that will definitely change our end game answer. So if I use PEMDAS for part C, I'm going to take 81 to the 1/4, and then I'm going to multiply it by -1. All right, but I've got a rational exponent. I see my denominator is 4, so this is going to be negative of the 4th root of 81. And then it's on me to simplify this, right? And 81, if we break it down, right, we know it's 9 and 9, which is 3, 3, 3, 3. So this becomes the opposite, or the negative, of the 4th root of 3 to the 4th. When I have a root that matches an exponent, those cancel out. Those are inverse operations of each other. So the 4th root of 3 to the 4th is 3, and then I have that negative in front of it, so this is negative 3. Now on the flip of it, right, if I do this, this is saying get me the 4th root of negative 81, right? So denominator's 4, that becomes my index, and then because this entire term, this entire number is in that parentheses, that becomes my radicand. And when I say radicand, I mean the stuff under the radical. But this brings up a domain issue, right? We are not allowed to take the even index to a negative number. That winds up being imaginary. So since we're just going to deal with the real world right now, this does not exist. I'm going to put this as a little DNE because it is not a real number. It is a complex number or an imaginary number. Okay. All right, now I'm going to scooch this up just a little further so we can get these last couple in view. And I do want to start to mention here, you also see the negative in part E is under that, or is in that parentheses. And I have a 3 as my denominator. So what this is going to turn into is I'm going to have a cube root of negative 64. But the thing is, you are allowed to take an odd index to a negative number. We can take the cube root of a negative number. We just can't do it when it's an even index. We can't take the square root or the 4th root or the 6th root. And if you think about 64, and let me actually scooch this up just a bit more so we can see all of this. All right, if I want to start to think a little bit more closely about the way negative 64 breaks down, let me do a little side quest here. Negative 64, right? I could think of that as negative 4 times 16, right? And you can think of this as 4 and 4, or really, if I want to get fancy, this is negative 4 and negative 4. So what's happening with the cube root of negative 64 is this is the cube root of negative 4 cubed. Odd index of 3, or I shouldn't even say odd index of 3. Index of 3, exponent of 3, those cancel out, and you get the negative 4. And if you're thinking, ooh, I don't know that I would have broken this down into negative 4, negative 4, negative 4, just keep in mind with the odd, if you have the odd index with a negative, that negative can jump out. So what I mean by that is I could also just simplify this to be negative cube root of 64, right? And then it's the opposite of the cube root of 4 cubed, right? Those cancel, and that leaves me with negative 4. So that might be a different way, or maybe depending on how your brain works, that might be an easier way for you to simplify that expression. All right, let's take a look at this one, okay? So I have 32 raised to the 1/5. So just to remind us, as we've gone through example 1, every numerator was 1. Even if it happens to be in this fraction, but this rational exponent, every numerator was 1. We're going to change that in a little bit. So this becomes the 5th root of 1 over 32. All right, and you are allowed, if you want, it depends on how you want to look at this. You can distribute that 5th root to the numerator and denominator separately. So what I mean by that is you could do this as the 5th root of 1 over the 5th root of 32. That is absolutely fine. Okay, and then what you could do is the 5th root of 1 is going to be 1. And if you break down 32, right, we've got 16 and 2, 4 and 4. Ooh, let me put a little separation here. This is going to get crowded. 2, 2, 2, 2. So you can see we have 1, 2, 3, 4, 5 2s. That's not by accident. I picked that number intentionally. So this becomes 1. Ooh, and we might be running out of room over here. But we're going to have 1 over the 5th root of 2 to the 5th. And again, the 5th root and the 2 to the 5th are going to cancel. This ultimately leaves you with 1/2, right? And some of you might like it this way instead. You might think, well, I'm just going to break down 1 over 32. So you might say, well, this is the 5th root of 1 over 32, which is like saying the 5th root of 1/2 to the 5th. Because again, if I took 1/2 times 1/2 times 1/2 times 1/2 times 1/2, I have 1 to the 5th on the numerator, which is 1. 2 to the 5th, right? 2 times 2 times 2 times 2 times 2 is 32. So 1 over 32 is the equivalent of 1/2 to the 5th. I've got 5 as the index, 5 as the exponent. Those cancel out and leave me with 1/2. Okay, so we took a look at some expressions with rational exponents where the numerator was always 1. And when we get to example 2, we're gonna change that. We're gonna build on this. So the denominator always maps to the index, and what you're gonna find out in a little bit is the numerator maps to the exponent of your radicand. And I'll explain that a little bit better on the next example. Okay, thanks so much. Bye.